So now that you guys have learned how to run hypothesis tests looking at one proportion, we want to move on to running a test comparing two different proportions. So I showed you a few examples of what a two-proportion test might look like. In a two-proportion test, we're comparing two different groups of things. So we may compare men versus women, or a control group versus a treatment group. We may compare minorities to majorities, or we might compare different subsets of the population. So we need two different groups of things to compare, and then we can test a claim. So for example, we can compare the statement, women smoke more than men. We could go out and sample 100 women and ask them whether or not they smoke. We can then go ask 100 men whether or not they smoke, and we can compare the sample of women who smoke to the sample of men who smoke. That's what we're doing when we're comparing two proportions. So a two proportion z-test compares two percentages, and these are much more common questions than the one proportion test, because often we're trying to compare two different groups of things. So like I said before, maybe we want to compare the effectiveness of a drug, and you need to compare it to a placebo or a control group. Maybe we want to test the effect of a policy, so we would look at the effectiveness of it before and after to see whether or not the policy had any impact. You could also use a two proportion test to compare, let's say, your favorite sports teams and see whether or not their proportions of wins is greater between team A and team B. So that our parameter of interest has changed a little bit. Before, our parameter of interest was just one proportion. Now, our parameter of interest is the difference between two proportions. So we're looking at the difference, and the way you calculate a difference is you subtract one proportion from another. So this term here is the difference between group 1 and group 2. What we're going to assume is that the two groups are the same. So that means if they're the same, the difference is 0. And so we're assuming they're the same, the difference is equal to 0. That's always going to be our null hypothesis. The alternatives then is that one group is greater than the other. So in this first alternative, group 1 is greater. In the second alternative hypothesis, that's stating that group 2 is greater. And the third statement, that is our two-tailed test, that is just saying the groups are different. It's not saying which group is greater. It's not putting direction on this, which is why there's a two-tailed test. It's just saying that the two groups are different. We can't say that they are the same. So that's how you set up the null and alternative hypothesis. It's based on the wording of the question and which group you think is greater. That's the alternative hypothesis. The next thing we have to come up with is our model. And again, we're going to assume the normal model for this distribution. The distribution of the parameter of a difference between these two groups. It's going to be centered around this true difference. So notice that these don't have hats on top of them. It's indicating that this is the true difference between these two groups. And if this is the true difference, then samples are going to vary. Some samples are going to show a difference that's greater. Some samples are going to show a difference that's less than this true difference. The standard deviations captures that variation in samples. That's why we have hats on these terms. It's that we're saying this is the standard deviation of that sampled difference. It's going to be based upon the proportion of the two groups, the true proportions. Now, in reality, we don't typically know what these true proportions are, so we're going to use our samples to estimate them, and they're going to give us a standard error. So as I mentioned before, we don't know what the true proportions are, so we have to use our sample to estimate the standard deviation which is why we get a standard error instead. Now there are two different ways to calculate a standard error, and your book reviews both of them. I will show you here how to calculate what's called the pooled standard error. So the pool standard error assumes that the two groups are the same, and that's what we're doing under the null hypothesis. We're assuming group 1 and group 2 have the same proportion or the same rate, and so we're going to use that information to calculate this, what's called the pooled proportion. Once we have that pooled proportion, we can calculate our standard error and use that in calculating our z-statistic. So our z-score is just going to be our sample difference minus 0. And remember, we usually put our hypothesized value second. And here, our hypothesized value is 0. So that's why we're subtracting 0 here. And then we're going to put our pooled standard error on the bottom. So let me review how you calculate this p-pooled. To calculate the p-pooled, what we're doing is we're assuming that the two groups are the same. So we're just going to pool the two groups together. Here I have the total size of group 1, the total size of group 2, and how many successes are in each of them. So if we're looking at women who smoke and men who smoke, the success would be the number of women who smoke, and success 2 would be the number of men who smoked. N1 and N2 would be all the people that we survey. If we think they have the same rate of smoking, then we can just pool them together, and that's going to give us p-pooled. Once we have that p-pooled, we can get a q-pooled as well, so it's just 1 minus p-pooled. And then we need to divide by the sample size, so we need to take into consideration that we have two different sample size. As I mentioned before, if we wanted to survey and compare men versus women, we could sample 100 women and 150 men. It doesn't matter if their sample sizes are different. We can sample two different sizes, and our standard error accounts for that variation in sample size. So let me go over a problem so you can see how the mechanics of this work. Here we have a problem in which a clinic reports the following statistics for the number of live births for women over the age of 38 and under the age of 38. They've sampled more women under the age of 38 because it's more common for women under the age of 38 to have births and to be pregnant than it is for women over the age of 38. What we want to test is we want to test if there is an actual difference between these two women as the rate of the live births that they have. So I want to start by calculating my sample proportions. I have 3 sample proportions. First, I have the proportion of women under the age of 38 who gave birth to live children. So 47 of them were live out of the 165 women who were pregnant. That's a success rate of 28%. For women over the age of 38, it's lower, it's about 5%. When we pool them together, we're putting all of the live births over all of the women, and that's a success rate of only about 21%. Now we want to test to see whether or not these two types of women, women over 38 and under 38, is different. You can see here the rates are different, 28 compared to 5%, but these are just samples of the population. We want to know, is the population different? We recognize that samples vary, and so maybe this difference that we see is just due to the fact that we're sampling. So what we're going to do is we're going to assume that the true difference is that there is no difference, that they are the same, the true proportions are the same. And we're going to try to find evidence, our sample is our evidence, that they are in fact different. We're going to run a z-test, and in order to run that z-test, we need a standard error, and we're going to utilize the pool standard error. So the way this is calculated, again, we're square rooting, because that's always how we start with a standard deviation or a standard error. And the way we calculate this is we're going to use the p pooled, so that pooled proportion, to calculate not only the sample size for the women under 38, but also for the women over 38. So this is just p times q, where q is just 1 minus p, and we divide by the sample size for group 1, and then we do the same thing and divide by the sample size for group 2. So we're essentially adding these two variances together, and again, the two groups have different sample sizes, so we have to account for them. That's going to give us a standard error of 0.05596. So now we want to go on to calculating our z-score. And the way our z-score is calculated is we calculate our sample difference first. So the observed difference goes first. So we have the difference between women under 38 compared to the women over 38. And then we subtract our hypothesized value. So our hypothesized value is that there is no difference, and so we're just going to subtract off 0. For most of these problems, you're going to subtract off 0. It would only be if you thought that there was some a priori difference. So for example, if you're comparing men and women's wages and you thought that women made 20% less than men, the difference would be 20% and you would have something that's different from 0. But for most of these problems, you're going to assume that the two groups are the same, and so what you subtract off will be 0. Once you have that top part, you divide by the standard error. So you always divide by either a standard error or a standard deviation. Here we're going to divide by the standard error, and that's going to give us a z-score of 4.174. The next step then is to calculate the p-value for this z-score. Remember that our alternative hypothesis determines the sign in that probability. So when we're saying that they are different, that means we're saying they are not equal. And so we're saying the true difference is not equal to our hypothesized value. I'm sorry, the true difference is not equal to the value that we observe. And so the value that the observed difference is 0.2317. That's equivalent to saying the z-score that we calculated is not equal to the absolute value of 4.174, the value that we calculated. So we want to see how unusual is this sample that we've observed if the null hypothesis is true. Again, we're going to use our rule for the two-tailed test when the alternative hypothesis is not equal to. So we take our positive z-score, we reach up, we try to find the probability of everything greater than that positive z-score, and then we times it by 2 to get the upper tail, and we get still a really, really, really small probability, basically a 0 probability. So the conclusion is that because our p-value is really tiny, it's unlikely that the null hypothesis is true. So we have made a bad assumption, and our p-value is less than the predetermined alpha level. So our alpha level was 0.05. Because the p-value is less than that, we reject the null hypothesis. We find evidence to suggest that there is a difference between women under the age of 38 and women over the age of 38 in which the rate that they have live births at this clinic. So these are the basic steps that I took in calculating this and performing this two-proportion test. The first is to find and calculate the sample difference. So you need to figure out what your sample is, the sample for group 1 and the sample for group 2. They may be different sample sizes. It's important then to calculate that pooled proportion because you're going to use that pooled proportion to calculate the pooled standard error. Once you've done that, you can determine the alternative hypothesis. So the null hypothesis is that they're the same, so group 1 and group 2 are equal, so the difference between them is 0. The alternative hypothesis may say that one group is greater than the other. So if group 1 is greater, this difference has to be positive. If group 2 is greater, this difference has to be less than 0. We can calculate the z-score using that formula I showed you earlier, and then from that z-score we can find the p-values from our z-tables and our z-calculators. Finally, in the next video, I'm going to go over a few more problems so you can see how I calculate this out.